Welcome to the deep dive. Today we are diving into, well, one of the biggest scientific quests out there, achieving limitless clean energy from nuclear fusion.
It really is the ultimate energy dream, isn't it?
Absolutely. For decades, it's held this incredible promise, minimal long-lived radioactive waste, absolutely zero meltdown risk, and fuel that's basically everywhere, deuterium from seawater, lithium for tritium.
And the reaction itself, deuterium tritium or DT, it's just immense.
Right, releasing 17.6 megaelectron volts of energy per reaction. And the temperatures, they're astronomical, 100 to 150 million degrees Celsius, hotter than the sun's core.
It's a vision that's, captivated scientists for generations.
Yeah.
Driven so much research, so much investment.
And it's a big but.
Yes, exactly. Despite all that effort, a few really fundamental challenges have kept fusion power, just out of reach, always seeming like it's just around the corner.
Which brings us neatly to the focus of this deep dive,
Huh.
the Synergetic Plasma-Tokamak, or SPT. Now, this sounds different. It's presented as an integrated reactor architecture, kind of holistic solution.
That's right. Developed and proposed by Mr. Shahryar Ghiasi. And what's really interesting, I think, is that it's not just tackling problems one by one.
Okay, so it's about how they connect.
Precisely. Recognizing the interplay between these challenges. So for you listening, our mission today is to explore those persistent roadblocks and then understand how this SPT concept aims to overcome them by integrating recent breakthroughs. They're aiming for, well, a genuine paradigm shift.
Okay, let's set the stage then. What are these stubborn problems, the ones that have kept fusion mostly in the lab? Our sources highlight 4 key barriers the STT is designed for. First up, plasma instability.
Yeah, think of trying to hold that super hot plasma, that miniature star, with magnetic fields. It's like using invisible ropes.
And sometimes those ropes fray.
Exactly, leading to disruptions, sudden shutdowns, not ideal for a power plant.
Not at all. Okay, second barrier.
Material degradation. This is a big one. You've got this constant bombardment of high-energy neutrons and intense heat hitting the reactor walls.
Neutrons literally knocking atoms out of place.
Yes, causing damage over time, weakening materials. And the heat fluxes. We're talking potentially over 10 megawatts per square meter. Imagine thousands of heaters focused on one small spot.
Okay, intense. Which leads to the third challenge, I guess. Low power density. Is that why reactors like ITER are just so enormous?
It's a major factor. Yes, you need that huge volume to get significant power output with current approaches.
And finally, number 4, operational disruptions. Just keeping the reaction going smoothly, continuously for long periods. That's been tough.
Incredibly difficult. Sustained operation is key for reliability.
Right, so instability, material wear, low density, and keeping it running. That's the mountain to climb.
And this deep dive is about how the SPT proposes to climb it, bringing together several innovations to make fusion compact, efficient, and importantly, economically viable.
All right, let's get into the first of these innovations. It's called the symmetry-optimized Stellarator-Tokamak hybrid configuration. Bit of a mouthful.
Ah, yes it is.
Now, people following fusion will know Tokamak's powerful, but prone to those disruptions we mentioned. And stellarators, they're more stable, but notoriously complex. So, a hybrid. How does that work?
This is where really advanced computing comes into play. They're merging the best of both worlds, essentially.
Using computers to find a sweet spot.
Exactly. Leveraging symmetry theory from places like UT Austin and Los Alamos, plus machine learning. They use these tools to design magnetic fields that are quasi-symmetric.
Quasi-symmetric. Okay, what does that mean in practice? Less leaky.
Precisely. Think of it this way. A standard tokamak field isn't perfectly uniform, so particles drift out, losing energy. Stellarators try complex shapes to fix this. Quasi-symmetry means the field is computationally designed, so particles act like they're in a perfectly simple symmetric field, even if the coils look complex.
Ah, clever. So the particles are fooled, in a way.
You could say that, and the result, they estimate it reduces particle loss rates by a massive 90% compared to conventional designs.
90%. That's huge for efficiency.
It is. Plus, this method calculates the stable magnetic configurations, the equilibria, 10 times faster than older simulations. So you can iterate and optimize much quicker.
Okay, that's the field shape. But I saw something about adaptive magnetic surface control, sensors inside the coils, sampling at 100 kilohertz.
Yeah, that's the real-time control aspect. Imagine tiny magnetic sensors embedded right in the superconducting coils. They pick up the slightest wobble or perturbation in the magnetic field almost instantly.
And then?
Then reinforcement learning algorithms, AI, analyze that data, and adjust the currents in the surrounding magnetic field coils. And they do it incredibly fast, within less than 10 milliseconds.
10 milliseconds. So that's
Yeah.
faster than instabilities even really start to grow.
That's the idea. It's like preemptively correcting a wobble before it becomes a major problem, catching it super early.
Wow. And the coils themselves are different too. Additively manufactured coils, like 3D printing.
Exactly. They're 3D printing composites of copper and high-temperature superconductors, HTS.
HTS, right. Those work at slightly less extreme cold temperatures.
Correct. And 3D printing lets them create really precise, complex shapes needed for that quasi-symmetry. Plus, it apparently cuts down resistive losses, wasted energy, as heat by about 40% compared to traditional superconducting magnets.
So putting innovation one together, this quasi-symmetric field, the super fast adaptive control, the special coils, what's the overall impact on the plasma?
The big claim is enabling steady-state operation at a beta of 40%.
Beta, that's plasma pressure versus magnetic pressure, right? Higher is better for power density.
Yes, higher beta means you're getting more fusion power for the cost of the magnetic field holding it in. 40% is very high, basically double the conventional stability limits for tokamaks. And crucially, the claim is this eliminates those major disruptive instabilities altogether.
Okay, eliminating disruptions. This feels like a fundamental shift for making fusion reliable as a power source.
It would be a game changer, yes, if they can achieve it consistently.
So that addresses stability. But what about handling the sheer brutality inside? The heat, the particles, particularly at the exhaust pipe, the diverter. Which brings us to innovation two, the cascaded liquid metal diverter with electromagnetic flow control. Cascadem.
Right. The diverter is arguably the most challenging component in terms of materials. It faces the brunt of the heat and particle exhaust. We're talking projected heat loads over 20 megawatts per square meter in compact designs.
Just punishing, so a liquid metal solution.
Yes, the SPT proposes using a flowing film, multi-layered, of a liquid lithium tin alloy. LiSNO, about 15 centimeters thick, flowing at around half a meter per second.
Okay, so it's like a constantly refreshing shield. What does it do?
It does several things at once. First, it absorbs that intense heat flux. Second, the lithium breeds tritium, one of the fusion fuels, when neutrons hit it. That's the 6-lane alpha-T reaction.
Ah, fuel breeding integrated right in.
Smart. And third, lithium has a low atomic number, Z3, which means if tiny amounts get into the plasma, they don't contaminate it as badly as heavier metals would. The tin is added mainly to improve corrosion resistance at the high operating temperatures, around 800 degrees Celsius.
And low vapor pressure too, I assume, to limit that contamination risk.
Exactly. Very low vapor pressure is key.
Now, the heat management part sounds fascinating. Electromagnetic flow control, inducing vortices. What's that about?
So instead of just letting the liquid flow smoothly, they use electromagnetic pumps to deliberately create swirling patterns, like little whirlpools, within the flow. Toroidal vortices.
Why do that?
These vortices effectively spread the incoming heat load over a much larger surface area, they estimate 5 times larger. This drastically reduces the peak heat flux hitting any one spot.
Ah, spreading the load, so the peak drops.
Drops to less than 4 megawatts per square meter, according to the design, which is potentially within the tolerance limits of advanced materials like silicon carbide composites, the stuff holding the liquid metal system.
Okay, that makes sense for handling the heat. What about keeping the liquid itself clean or preventing droplets from flying into the plasma?
Good question. They propose using laser interferometry to constantly monitor the surface where the plasma meets the liquid. If it detects vapor starting to form or instability that might cause a droplet to eject,
Yeah.
it triggers counter-electromagnetic fields specifically designed to suppress that ejection, keeping the boundary clean.
That is incredibly sophisticated, like active droplet control.
It is. The potential impact here is significant. They suggest experimental validation points towards over a year of continuous operation without needing diverter replacement. That's a huge leap in component lifetime.
Huge for maintenance and economics. Okay, innovation 3, the cyber-physical HTS magnet system. We touched on HTS magnets, crucial for getting strong fields in compact reactors, but they have this risk, quenches. Can you explain that?
A quench is basically when a part of the superconductor suddenly stops superconducting. It loses that zero resistance property, starts heating up rapidly due to the massive current, and, well, it can potentially destroy the magnet. Very bad news.
Right, sounds catastrophic. How does SPT plan to avoid that?
It's a combination of prediction and protection. They call it a cyber-physical system. For prediction, they plan to embed thousands over 10,000 tiny fiber Bragg grading sensors directly onto the HTS tapes.
Fiber optics measuring strain and temperature.
Exactly. Continuously monitoring. AI algorithms then process this flood of data, looking for the subtle warning signs of a hot spot forming the precursor to a quench. And they claim these algorithms can predict a quench about 30 seconds before it actually happens.
30 seconds, that's
Yeah.
an eternity in magnet time. Enough time to react.
That's the idea. Enough time to initiate a controlled ramp down of the current or take other preventative measures. It's proactive, not just reactive.
Okay, that's the prediction. What about protection if something does go wrong locally? I saw this term. No insulation self-protection. Sounds weird. Don't you need insulation?
Traditionally, yes. But here, they propose removing the insulation between the turns of the HTS tape and the coil.
Why on earth would you do that?
It sounds counterintuitive, but it allows the current to instantly find alternative paths if one small section starts to fail or heat up. Instead of concentrating the failure, the current redistributes itself around the problem area.
So the coil protects itself by sharing the load immediately.
Essentially, yes. This NI, or no insulation concept, has actually been tested, notably by MIT and Commonwealth Fusion Systems, up to very high fields 20 Tesla. Their tests showed coils could handle significant overloads, like 150%, without damage because of this self-protecting feature.
Remarkable. And the cooling. Still needs cooling, right? Even HTS.
Oh yes, still very cold.
Yeah.
But HTS works at warmer temperatures than traditional superconductors, around 20 Kelvin, which is minus 253 Celsius.
Still freezing, but less extreme than liquid helium temperatures, maybe.
Right. And this allows them to use cryogenic free cooling. Basically, direct conduction cooling using microchannels with flowing helium gas right next to the HTS tapes.
What's the advantage there?
You get rid of the huge, complex, and energy-hungry liquid helium cryoplants. This significantly shrinks the overall magnet system volume, they say, by 60%.
Okay, so putting Innovation 3 together, predictive AI, self-protecting coils, more efficient cooling, what does this enable?
It enables incredibly strong magnetic fields, 25 Tesla, in a compact machine, a major radius of just 1.8 meters. And that strong field in a small volume is key to achieving that projected power density of 50 megawatts per cubic meter. That's 10 times IDEA's target power density.
10 times in a much smaller machine. That really highlights the compact aspect.
Exactly. High field is the enabler for compact high-power fusion.
Which leads us to the final piece, Innovation 4, the radial neutron reflector with spectral shifting. We talked about neutron damage. Those 14.1 MeV neutrons are nasty.
They are. They cause displacement damage, knocking atoms out of the structure, and transmutation, literally changing elements within the material. This degrades the reactor components over time, especially the first wall facing the plasma.
A major lifetime limiter? So how does the SPT shield against this?
It's more than just shielding, it's active neutron management. They propose a graded tungsten carbide reflector.
I can see.
Tungsten carbide. Heavy stuff. Graded how?
Layers with different, carefully tailored porosity. This does two things. It reflects neutrons back towards the plasma, which can actually help the fusion process, but it also degrades their energy.
Slows them down.
Yes, through elastic scattering. It shifts the neutron spectrum, reducing the energy of escaping neutrons to below 1 MeV. This drastically cuts down the displacement damage deeper in the vacuum vessel, they estimate, by 70%.
70% less damage just by reflecting and slowing them. That's impressive.
It's like using the neutron's own energy against their damaging potential.
And there's also something about in situ void swelling compensation. What's void swelling? That's another effect of neutron damage. Over time, vacancies empty spots where atoms used to be clustered together and form voids, causing the material to physically swell and weaken.
Okay, how do you compensate for that in situ while it's running?
They propose embedding piezoelectric actuators within the structural components. These are materials that change shape slightly when you apply a voltage.
Right.
So as the material starts to show signs of swelling, these actuators apply a counteracting compressive stress, literally squeezing it back into shape, preventing the voids from growing excessively.
Wow, active structural integrity management. And fuel. We mentioned tritium breeding with the diverter, but is there more? Nanoporous carbon aerogel tritium harvesting.
Yes, this complements the breeding in the liquid metal. Tritium produced in other breeding zones, likely ceramic pebbles within the reflector structure, needs to be efficiently extracted.
And aerogel does that.
Carbon aerogels are incredibly lightweight, highly porous materials. Think like a solid sponge, but mostly air. They have a huge internal surface area. The design uses these aerogel matrices to trap the tritium gas as it diffuses out with very high efficiency, they claim 99.9%.
Ensuring you capture almost all the fuel you breed.
Crucial for fuel self-sufficiency. The overall impact of these neutron management and tritium strategies, they project extending the first wall lifetime to over 8 years.
8 years. That makes a huge difference for the economics, doesn't it?
Absolutely. That kind of component lifetime is essential for making fusion power plants economically viable. It contributes to their projected levelized cost of electricity, the LCOE, of less than 5 cents per kilowatt hour.
Under 5 cents. That's competitive with, well, almost anything today.
If achievable, yes, it would be a major breakthrough.
Okay, so we've covered these 4 big integrated innovations. Let's try to put the SPT in context now. How does it stack up against other big fusion projects we hear about, like ITER or maybe Spark?
Good idea. Let's look at size and power first. SPT major radius are 1.8 meters, targeting 200 mW fusion power and that very high power density of 50 mW per cubic meter.
Okay, 1.8 meters. Pretty compact. ITER.
ITER's huge, RO 6.2 meters, aiming for 500 mW fusion power, but because of its size, the power density is much lower, around 0.5 mW per cubic meter.
So SPT aims for less total power than ITER, but vastly more power per unit volume.
Exactly. And Spark, another compact design being developed by Commonwealth Fusion Systems and MIT.
Spark is our 1.85 meters, so similar size to SPT, aiming for 100 mW fusion power with a power density around 510 mW per cubic meter. Still high, but lower than SPT's target.
And a key reason SPT projects such high density in that compact size is that quasi-symmetry we talked about earlier. By reducing neoclassical transport heat and particle leakage by potentially 10 times compared to a standard tokamak of the same size.
It holds onto the heat and particles much better, allowing for more fusion in a smaller space.
That's the theory. It relies less on sheer physical size for confinement, unlike ITER, which needs its massive scale, partly just to meet the basic conditions for net energy, the Lawson criterion.
Okay, what about those critical diverter heat loads? We said SPT aims for less than 4 milliW per square meter with its 25 Tesla field. How does that compare?
It compares very favorably. ITER, with its lower 5.3 Tesla field, expects 10-20 milliW per square meter on its diverter. Spark, with a strong 12.2 Tesla field, projects maybe 15 to 25 milliW per square meter.
So SPT's liquid metal diverter, if it works, handles the heat much more gently, even with a stronger magnetic field compressing the plasma.
That's the potential advantage, yes. Lower peak heat flux should mean much longer component life.
And net energy, the ultimate goal. SPT is projecting net energy by 2032 and steady state operation.
That's their ambitious timeline, aiming for continuous steady-state power. Contrast that with ITER. Its first DD, deuterium-deuterium operations, are now projected around 2035, and its full DT pulses are designed for around 400 seconds, not continuous. Spark aims to demonstrate net energy in shorter pulses before SPT's timeline, potentially.
So SPT is really designed from the ground up for continuous power plant operation, if the tech works out.
That seems to be the focus.
And tritium breeding. Fuel self-sufficiency is non-negotiable for a power plant.
Absolutely. You need a tritium breeding ratio, TBR, greater than 1, realistically maybe 1.05 or higher, to be self-sufficient.
And SPT.
They project a TBR of 1.15 using that dual approach. The liquid aisle send diverter contributes about 0.4, and then lithium ceramic pebbles in the reflector blanket region contribute another 0.75.
1.15, that's a healthy margin. How does that compare to ITER's goal?
ITER's target is around 1.1 using test blanket modules, so SPT's integrated breeding design aims to comfortably exceed self-sufficiency while potentially simplifying the overall blanket structure.
Okay, this sounds incredibly advanced, almost futuristic, but the timeline they're suggesting seems very soon. What's the actual development plan look like?
It's definitely aggressive. The sources mention key milestones. Testing the HTS magnet cybernetics by 2026, a 1.5 scale prototype of the cascading liquid metal diverter by 2027, full demonstrations of the symmetry optimization codes by 2028.
Another big one.
An integrated SPT pilot plant aiming for 50 megawatts of fusion power by 2032.
2032, wow! That's less than a decade. How does that fit with, say, ITER's timeline?
It's interesting timing. If ITER achieves its revised DD operations around 2035, and projects like Spark provide net energy data sooner, the SP2 pathway, if successful, could potentially accelerate things significantly. It's also happening alongside this huge surge in private fusion investment, right?
Over $7 billion globally now, I think.
Something like that, yeah. So there's a significant funding ecosystem that could support and potentially speed up development of these enabling technologies if they show promise.
So, looking at the whole picture, The SPT isn't just one breakthrough, it's this convergence. It feels like a real paradigm shift across several areas.
I think that's a fair way to put it. You have symmetry-aware plasma engineering, moving beyond just building bigger magnets to really optimizing the magnetic field from first principles. That alone could cut auxiliary power needs by 30%.
Making the whole plan more efficient.
Then cyber-physical resilience.
Yeah.
Building the diagnostics and controls right into the components, especially the magnets, for that real-time self-awareness and mitigation. That's very different.
A smarter, self-healing reactor, almost?
And liquid integrated components.
Yeah.
Using liquid metals not just as coolants, but as active functional parts, heat transfer, breeding, shielding. That could simplify maintenance and enhance safety.
And finally, neutron spectrum engineering. Not just blocking neutrons, but actively managing their energy and direction.
It's about shifting from passive endurance to active control and management across the board. A truly integrated systems-level approach.
Yeah.
Now, it can't all be smooth sailing. What are the big remaining hurdles or question marks for this concept?
Oh, absolutely, challenges remain. Managing those plasma-liquid metal interactions, especially during unexpected events or disruptions, is still very complex. You absolutely have to prevent contamination.
Right. If the plasma collapses, you don't want liquid metal splashing in.
Precisely. And scaling up the additive manufacturing for these very large, very precise HTS coils is a major industrial challenge. It's one thing to make test coils, another to build a power plant's worth.
So manufacturing scale-up and edge plasma control with liquids.
Those are definitely key areas. But it's worth noting there are active research programs and developing technologies like advanced vapor shielding techniques and progress in 3D printing superconductors that offer plausible development pathways. They don't seem like fundamental physics roadblocks, more like very hard engineering challenges.
Okay, so wrapping this deep dive up, it really feels like the core idea behind the Synergetic Plasma-Tokamak isn't just a shopping list of cool tech, it's the integration, right? Combining these solutions to tackle fusion's biggest sticking points simultaneously.
That's the essence of it.
Aiming for that, you called it the elusive triad. Compactness under 2 meters radius, high power density over 50 milliliters per cubic meter, and crucial for a power plant, steady-state operation.
And connecting this back to you, the listener, and the broader energy landscape, we're entering a really interesting period. We expect critical data from projects like Spark, maybe mid-decade, and from ITER in the 2030s.
Right.
The SPT concept, grounded in recognized physics and emerging tech, presents a scientifically plausible, though ambitious, pathway to potentially demonstrate net energy fusion power within this decade.
And the impact wouldn't just be electricity, would it?
No, not at all. Beyond carbon-free electricity, the high temperatures involved open up possibilities for industrial process heat. Think steelmaking, chemical production, hydrogen generation, things that are very hard to decarbonize otherwise. It could genuinely revolutionize global energy systems.
Fulfilling that promise we started with.
Potentially.
Yes. So here's a final thought to leave you with. What if, after almost a century of fusion being the energy source of the future, what if that future is closer than we think? Not decades away, but potentially taking shape right now, perhaps even arriving within the next few years. What would readily available, clean, abundant fusion energy actually mean for our industries, our societies, our daily lives, and maybe even our concept of what energy is? Something to really think about.